So wish you all the best for the new year, and I hope Corona will be soon gone for all of us. And so let me introduce you today, our speaker. So our speaker is Professor Carlo Rovelli. Perhaps many of you know already his contributions in loop quantum gravity. He's one of the founding father of loop quantum gravity, along with Ashtaker and Lee Smolin. And not only that, he has actually contributed a lot in popularizing science, as we have been discussing, in various aspects of philosophical and theoretical, as well as different aspects of popularizing science. But today he's going to tell us something about quantum gravity and how can it be tested in a laboratory. And I leave the floor to now Carlo. And before that, I also welcome, I could see that today we have had a fantastic audience. We are covering perhaps from Europe, from North America, all the way from Australia, from India and Pakistan. So it has covered a huge range of interest in this talk. So Carlo, please, the floor is all yours now.
Thank you very much. Anupam, let me share my screen. And in the meanwhile, thank you and thank everybody. I see a lot of names I know, but a lot of names I don't know. So thank you for being here. Just one thing, if you want to leave your video on, it's very fine for me. At least I see some faces. You don't have to, but I prefer, and it's not slowing down Zoom. Zoom is not slowed down if you leave your video on, not your audio. Thank you, because so I'm talking to some faces. Let me go to the first page. Okay, so what I'm gonna do is to talk about these recent ideas and proposals about a quantum gravity experiment in the lab. And the way I thought of talking to you is that I gather from those of you I know and from what Anupam told me, that the majority of you are not people from quantum gravity, are people from quantum information or from quantum mechanical experiments in general. And since these experiments, these ideas are a fantastic opportunity and a fantastic coming together of two large domains of research, quantum gravity and sort of quantum information, quantum mechanical experiments. And the good of this is what we can learn from one another and the difference of perspective. I thought of giving my own quantum gravity person perspective on these experiments, in a sense stressing the differences in the way we view that rather than trying to hide them. Hoping that this is useful in both of us to learn about that. So this is the reason, the motivation. This is what I'm going to do. Now, as a premise, let me start before giving you my my plan by telling you how I got to this to learn about this. And 2 points. First, quantum gravity. You all know that we don't have a quantum gravity theory which is empirically supported and agreed upon the research community. However, and that will be a recurring theme of what I'm saying, quantum gravity is not, as sometimes seen from the outside, a mysterious dark region where we know nothing at all and everything is possible and who knows what's going on there. It's a domain of research which is very well developed, where a lot of things are known. Many ideas have been largely discussed and discarded theoretically, and as I will say in a moment, even experimentally. So there's a lot of piled knowledge of quantum gravity, and there is a, just a moment, are you hearing me well? Is that the sound is okay?
Loud and clear on my
Yes.
Okay,
Yes.
thank you, because I don't have my usual microphone. Okay, so what I'm saying is that we know things about quantum gravity, and there are theories of quantum gravity. Not many, but there are well-developed theories of quantum gravity. Loop quantum gravity is one of them. That's the point. That's the first point. Second point, The idea of quantum gravity in the lab is not new. There have been in the last decades, I would say, a quite numerous set of proposals, stream of proposals of how doing quantum gravity experiments in the lab. And since I do quantum gravity, I've been following carefully and, following the literature, scanning the literature, and every time there was a new idea, I plunged into it and studied it with attention. And I was always disappointed and non-interested. Why? Because precisely because we know what to expect about quantum gravity phenomena from decades of attempt to write quantum gravity theory, all those proposals were proposals of observing a phenomenon that is not expected from somebody who does quantum gravity. Of course, from the perspective of an experimentalist, well, why not trying? I mean, you don't expect it, but it might happen. But from a perspective of a theorist, of course it might happen. Everything might happen. I mean, you might try to look behind that chair and maybe there is a blue dragon there. So let's test it. Is there a blue dragon there? But as a theorist, I'm not interested in this experiment because, there's no blue dragon. If you happen to find a blue dragon, fantastic. I'll be excited. But I'm not putting my interest, attention to people searching blue dragons behind chairs. Let me give you an example without putting names or references. This was one idea. I think it was even tried to do that. If you have you shoot a photon through a glass, a thin glass, and from the perspective of the photon, this is like a potential barrier. You have enough energy to go through, so you go up and then you go down. And when you go up, you give a little kink to the glass, and when you go down, you give a little kink in the other direction. So the net transfer of momentum is zero, but for a while, there is a net transfer of momentum that then is observed for the photons. For a while, the glass moves, so there's a displacement of the glass. And you can compute this displacement, and you can measure it from the outside in some way. And of course, it's very small. And you can arrange parameters so that it's the order of the Planck scale. So the argument of the people proposing this experiment is, once it is Planck scale, we expect that the Planck scale space to be discrete or whatever, some quantum gravity phenomenon. So something peculiar should happen. And therefore, by measuring the photon later on, I should find this something peculiar. I should find some effect of the discretization of time or space in delta x. All right. Do we expect that? No, of course not, because the average position of the mirror is just the average position of its atoms, if you want. This is it's a variable which is the mean value of many positions. Is the individual little x's which might perhaps see a discreteness, but if you make the the average of many integers, you don't get an integer. You get a real number, and you can get an arbitrarily small real number by just averaging a lot of integers if there are a lot of zeros. So I don't know if I didn't follow that after some point. I don't know if this experiment was performed. If it found something, we would know. But I was totally ready to bet, my $5,000 that they would not see anything. And if they had seen anything, I would say, fantastic, now let's try to understand it. But, I was not interested. And this was I have a long stream of this, a long stream of notes saying, okay, this is not interesting, this is not interesting, this is not interesting. So this is why when the experiments that have all sorts of names, the last name that Anupam uses and I'm using here is quantum gravity induced entangle of matter, QGEM, came out, I looked at this and I was expecting to have the usual reaction. All right, so here is some other people who in the lab think that they are now seeing quantum gravity. Of course, they're not. So I studied the thing, and to my astonishment, I should say, that was not the case. QGEM is in effect with, if I have my $10,000 to bet, I'm bet that if the experiment can be performed, I'm not an experimentalist, so that's your job, guys. I mean, if you can do this experiment, if you do it properly, I bet $10,000 against $1 that the result will be positive. So you will see entanglement, right? So suddenly, this is enormously interesting because this is indeed a quantum gravity realistic experiment in the lab, which is not like, you know, let's see if there's a blue dragon behind the chair. It's, we do believe there is a dragon there. I do believe there's a dragon. Let's go and see it. Okay, that's a premise. Now, this is what I plan to do. Each one of these points is fast, except a few ones. So there are many, but they're fast. First, I started by saying that we know a lot of things about quantum gravity, so I'll just super fast say where I think we are, what is the empirical information about quantum gravity, and what is the theoretical ideas we have, and so what are the empirical open questions. I will say why QGEM is interesting specifically, and then I will analyze the QGEM the way I view it from my perspective, what is really going on physically there, and address some of the confusion which I believe is the literature relating age, degrees of freedom, the role of virtual gravity, and things like that. And then depending on this time at the end, I will also take one slide to talk about an idea of a relativistic version of QGEM, which would be a possibility of going beyond this experiment without too much need of improving sensitivity to test something which is different and truly related to relativistic quantum gravity effect. So let me start from the first. What do we know about quantum gravity? And first, what is the current empirical information about quantum gravity? Sometimes you're tempted to say, oh, zero. Not at all. We have all sorts of empirical information about quantum gravity. First, obviously, we have all the empirical information about all the phenomenologies that support general relativity and obviously quantum mechanics. Now, this plus the requirement that the theory is consistent, quantum gravity theory, that there is a consistent quantum gravity theory, is an extraordinarily tight theoretical constraint. Extraordinarily tight. I want to insist that. It's absolutely false, the idea that everything will be possible theoretically, okay? There are very few possible things. People have studied quantum gravity for decades, and the number of possible quantum gravity theories are, you can count on the fingers of one hand, and those well developed enough, you can do calculation, you can count on the 2 fingers, perhaps, or 3, I don't know, no more than that. Because whatever you try to do, it seems a great idea, but it either contradicts something we know about GR, or contradicts something we know about QM, or it is inconsistent. Plus, of course, or it has ultraviolet divergences, or this, or this, or that. So the problem of quantum gravity is not an embarrassment of richness. It's a very tied, almost mathematical well-posed problem, right? Is there a set of equations which is consistent, and in particular, give the phenomenology of relativity and give the phenomenology of quantum mechanics? That's the problem of quantum gravity. Now, beyond that, there's far more we actually know specifically about quantum gravity. Because something here is, oh, you know, quantum gravity phenomena are super high energy. What is it? Planck energy is 10 to the 19 GeV. And, you know, particle physicists at most CERN, they go to 10 or 10, I don't know, 10 to the 4 GeV. So there are, whatever, 15 order of magnitudes away from quantum gravitational phenomena. That's bullshit. Because even in particle physics, proton decay, which is a beautiful experiment that ruled out SU5, and it was a very successful experiment, it tests the phenomenon, which is just the order of magnitudes from the Planck energy. It's not that the only thing you can do in nature is squash particles one against the other. But specifically on quantum gravitational phenomena, in the last decades, there have been an astronomical campaign observation of astrophysical phenomena that have ruled out quantum gravity theories by observations at energy which are above the Planck energy. And these are the Lorentz violating quantum gravity theories, which were quite popular 10 years ago, or Java theory and things like that. They have put in strong empirical difficulty from a campaign of actual astrophysical observation. Another much more recent example is with gravitational waves and the neutron star merging. The arrival almost contemporary of electromagnetic and gravitational signals have ruled out a large number of alternatives to GR, which were also motivated by hoping being good to quantum gravity. So there are a lot of experiments done already which cut out the space of possibility in quantum gravity and tell us something about how nature works in that regime. And then there are, of course, things which are largely studied in the literature, like the effect of early universe region where the density rho, it's Planckian on the CMB. There are models for dark matter, for some cosmic rays that use quantum gravity phenomena. So we can say, well, this is cannot happen. This is a lot of work in process. And of course, then there is the thing in the lab, which, as I will say, have to do with the fact that the mass Planck is at the order of microgram. So Planck energy is very high, Planck density is very high, Planck time, Planck length are very small, but the Planck mass, it's in a very accessible domain, which is a microgram. So what are the current theoretical possibilities? Now let me stress one thing. We have a theory which is effective perturbative quantum field theory of general relativity, okay, which is considered reliable by almost everybody working in quantum gravity and fails when you have phenomena at the energy of the Planck energy. Now, it doesn't make us too happy, because the phenomena we are most interested upon, what happened at the center of the black hole or the early universe, are precisely at super high energy. But this does not mean that we don't have a theory for lower energy quantum gravity phenomena. We do, and it's not just linearized general relativity, it's full interacting non-perturbative general relativity quantum using the techniques of effective quantum field theory. So you can renormalize, you can compute, you can do stuff. And I would say everybody I know and whose science I respect, who works in quantum gravity, think that this is reliable predictions. Of course, we haven't tested those predictions yet, but it would be extraordinarily surprising if they weren't realized. So I think, for the perspective of a theoretician, there are plenty of things in the world we don't know, and some of the things we know could be wrong, but there's plenty of things we know, and these include what happened in quantum gravity phenomenon unless you go to very high energy. All right, so we know stuff about quantum gravity. Now, in this outside the domain where effective perturbative quantum field theory of general relativity does work, we know more because there are tentative theories. There's loop quantum gravity, which give us a very good picture of the Planck scale structure of space-time. So what is quantum space-time in the small, and it gives transition amplitude, so the dynamics. Unfortunately, with expressions are very complicated to compute, and they haven't been tested. And the string theory, which gives doesn't give a picture of quantum space-time, but gives us scattering amplitude, consistent Lorentz invariant at arbitrary energies, well-defined, finite, again, that haven't been tested. But, you know, it's possibly that the two the quantum gravity string theory also get the same result for scattering amplitudes. Nobody knows. The structure is similar. And certainly both agrees with effective perturbative quantum field theory at low energy. Otherwise, they're wrong.
Carlo, I think there's a question by Jonathan, who has raised a hand. So
yes, Jonathan. If there is a short question, I'm happy to discuss it. This is for discussion.
Yes. When you say that the predictions of low energy effective theory, what are there particular effects you have in mind, whether experimentally realizable or not? Are there any, for you, predictions of effective quantum gravity?
Yeah, sure. I mean, take two protons and have them scattering and gravitationally, Or take a neutral particle, have them scattering gravitationally, and you can compute the scattering amplitude entirely. To various order in GH bar, you can do next ordering. You can compute the correction of the Newton potential. But the Newton potential is not just 1 over r, because there are H bar correction, well, there are relativistic correction, sort of the one from GR, but then there are also H bar correction. This has been computed by Donog, by a number of people.
I guess, I mean, I don't know how, how, I guess the correct word is phenomena, any phenomena that's, or like, if you had to say, what have we learned from effective field theory, low energy effective field theory? Is there something you would be able to say, or?
We've learned that there are quantum corrections to scattering amplitude and to Newton potential and other phenomena like that. Perhaps I'll ask, perhaps when I talk about the lab experiment, there will be another piece of the answer that you will find more convincing, and then you can come back with the same question. There's another hand I see. Ori?
Hi, I have a short question.
Yes.
You mentioned a few minutes ago that there is an astrophysical constraint on the quantum gravity effects, rightly from, for instance, gamma ray burst. This should sort of constrain what you said about a quantized space-time, because we don't know really if quantum gravity needs a quantized space-time.
I did not understand the question. What is the question? Sorry.
My question is that is the presence of a does quantum gravity needs quantized space-time? This is my question.
Ah, good. Well, quantized means different things. If you, I'm going to talk about that also. All theories of quantum gravity consider the gravitational field as a quantum field. So it's quantized, okay? And all fields of quantum gravity consider the gravitational field as the object that determines the geometry of space-time. So the geometry of space-time is quantized, okay? Which means it obeys standard quantum theory properties. This is true in string theory, this is true in effective perturbative GRs, this is true in loop quantum gravity. In some theories, you are capable of doing specific calculations about geometrical properties. For instance, in loop quantum gravity, you can compute the spectrum of some geometrical quantities, and you get it discrete. So then you have a quantized in the sense of granular, discrete bits of volume, for instance. In string theory, you cannot do this calculation. So it might be that there is the same predictions, but nobody's been able to do that. I mean, there are things you can compute in loop quantum gravity, you cannot compute in string theory, and vice versa. String theory, you can compute scattering amplitude, which is horrendously complicated in loop quantum gravity. In loop quantum gravity, you can compute eigenvalues, which are horrendously difficult in string theory. So if by quantize, you mean that the geometry is a quantum thing, yes. I mean, all theories of quantum gravity predict that, all. I insist, all. If you mean specifically that there is a discreteness in the small of the Planck scale, there are hints that in string theory is the same thing. Calculation by Amati, Ciafaloni, Veneziano some time ago, but there's no specific calculation. In loop quantum gravity is a very specific calculation that shows that there is no length beyond the Planck scale.
Okay, I have comments, but maybe later.
Okay, good. Yes, because I will address some of these things later on. So I hope there is enough time for discussion then to come back to these things. I'll be more specific in a moment. Now, beyond this large said, because I mean, the loop quantum gravity community, the string community, the people doing symptotic safety, the people doing other, this is a vast world with differentiation and disagreements about specific points. There are also some marginal ideas which escape that, which I mention here. Well, not too marginal, but a little bit the Lorentz violating theories that I mentioned already, which have been put in strong difficulty by astrophysical observations. There are the ideas, and then there are three things which I want to discuss a little bit more in detail. There's the gravity-induced collapse, right? Roger Penrose's idea, and the Penrose does a model and so on. Now, that's a possibility that, in a sense, is outside the quantum gravity consensus, the large quantum gravity consensus. Let me say, I have to plug my computer, it's telling me that it doesn't have enough battery. Sorry, apologies. Yeah. Let me say that first, there is no theory of quantum gravity-induced collapse. There's an idea that it could happen. A lot of people try to transform it in a theory. I mean, a theory consistent with general relativity, not a theory consistent with Newton mechanics, a real theory, consistent with what we know about the world. For instance, that was Ashtikar's thesis when he was in Oxford many years ago. Nobody has been able so far to do it. Is it possible? Well, I would not bet all my wealth against it, but I would easily bet $3,000, $5,000 that it doesn't work. There is some possible preliminary indication against it from some experiment. I don't want to go into it. Is it worth testing it? Yes, of course it is, because, you know, who knows? Roger Penrose is one of my idols in science. It's total genius. It's fantastic results all over. I've used his results in my physics at length. I consider him a wonderful person, a friend. But I don't think he's right there. Do I know? Well, of course, no. Nobody knows. But let me stress, is an extraordinary marginal and minority opinion, the idea that there could be a quantum gravity-induced collapse, not really considered by almost anybody who works in quantum gravity. Still, was to test. The next point is classical gravity to quantum matter. And this is even stronger. The idea that you could have a consistent theory with classical general relativity, classical geometry, and quantum matter was much studied in the 70s. I remember because I was a student at the time, and there was many talks, and it was completely discarded on consistency ground. Recently, it has been resurrected with the idea that perhaps one can circumvent the arguments that were given back in the 70s and the 80s. The argument is the following. There obviously is a consistent theory of some classical variables and quantum variables within the approximation in which you can disregard the interference of the variable that you consider classical, right? I mean, we use it every day. And this can be done, and a very beautiful formalism can be put up to describe what happens, describing a classical variable statistically, and having a master equations that somehow tells you how things evolve within this approximation. Then what you can do is to take the equations that tells you the domain of validity of this approximation, okay, and imagine that these are fundamental equations, so that in nature you're always within approximation. And that's the idea. And that's total nonsense, because those equations don't give you, you don't have a theory that give you that falls to stay within this domain. You can impose it. You can say, well, imagine that God somehow forces always things like that. But if you do that, you're working with an hypothetical theory that you don't know, that contradicts everything we know about nature, okay? That violates quantum mechanics, violates relativity, violates everything, right? So could it be? Of course, could it be? I mean, there could be blue dragons behind my chair. Am I interested in it as a fundamental theory, as a hint of what could happen? No, zero, zero. Is it an interesting formula? Yes, it's an enormously interesting formula because it allows us to study what happens when there is no interference phenomena between the variables that you consider classical, which is a huge domain. So it's a fantastic tool. It's not a proposal about what happens. And if somebody tells me, yeah, but imagine those equations that restrict the domain of validity are fundamental, so we can test them, I'll say, well, if you want to waste your time, do it. But I don't think this is so interesting. I'm going strong because I want to tell you how I and people in quantum gravity think about that. And that's basically the last point. From the point of view of a theoretician, if the question is, are you going to entertain the idea of a classical theory of the gravitational field geometry in in quantum matter, I would ask, which theory? Give me a theory, a hint of a theory, a beginning of a theory, but not a priori statement that this is the case, which is based on nothing, in my opinion. So what are the open empirical questions? First, can we differentiate at the Planck scale between the tentative theories we have? And can we, if we believe that there are quantum gravity phenomena, can we see one? And until recently, the hint was you have to go to high energy, and the QGEM, to my surprise, are saying, no, you can see a quantum gravity phenomena without going at very high energy, because there's another parameter, which is the Planck mass, which tells you that something can happen at lower energy. In fact, can happen in the non-relativistic domain, and we'll see what it means. So why is QGEM interesting? This is going to be fast. First of all, and if you have to remember one thing about this talk, just remember this. I think, and I want to state very strongly, that if the QGEM experiment is done and has a positive result, so if there is the effect, and if there's no actual distance in nature, which is what every theoretical physicist believes strongly. So if it's not true, we have all it wrong about nature, which fantastic. I mean, if we have all it wrong, good, it would be interesting. But, you know, it could be that there are blue dragons behind my chair, but I don't believe there are. And if the gravitational field determines the geometry of space-time, which is what no theoretical physics doubt, it's just something we've learned. Like, you know, the Earth is round, the Earth is moving. Humans have common ancestors with apes. It's something we have learned. The geometry is an effect of the gravitational field. So if these three things happen, two of which are extraordinarily reliable as far as we know about nature, and the third hasn't happened yet, then geometry, we have seen geometry in a quantum superposition. So in order for geometry not to be possible to be put in quantum superposition, it has either that we have wrong something fundamental about special relativity, or we've wrong something fundamental about the nature of geometry and gravity, or that the QGEM it wouldn't work. All right. So the experiment, in my opinion, a positive result of the QGEM experiment proves, without any reasonable doubt at this point, we are scientists, so there's always some doubt, but it proves without its meaning is that there's a quantum superposition of geometries. As in addition, it would put constraints in the idea of this classical gravity plus matter, even if there's no theory, and it would put constraint on the quantum gravity-induced collapse, which is not the same thing, of course, but is somehow related. All right. So last reason of interest is that the experiment has to do the Planck mass. I'll come back. But the main parameter of the experiment is the difference of phase between the four branches in the quantum state, which I'll write this equation in detail later on, but if you know it, it's just proportional to Newton constant over a Planck constant, the mass of the particle, the superposition, the time they stay in superposition, the distance they are in one branch, and this is proportional G over H, not G times H, which means Planck mass essentially. In fact, if you write this, if you multiply this by C and C, the speed of light, this Ct over d is a dimensionless parameter that you can think as some apparatus parameter. This is how long the mass are kept next to one another at distance d, and then the key factor is m over m Planck. So it's m Planck which is coming here, the relevant parameter. This is it's a phenomenon which is g over h, and that's why it survives in the c going to infinity limit, because c disappears here. So it's a no-relativistic phenomenon. Okay, so how am I with time? I've used a little bit more than what I wanted. Let me go to the actual discussion of the experiment itself. This is the idea of the experiment. I think that many of you know it well, so I'm not going to go in any detail. You have a particle 1, which you quantum split. You put in the superposition of two positions. A particle 2, you do the same thing. Both of them, then you bring together the two branches. So you have 4 branches, sort of left, right, left, left, right, right, and right, left. And in one of the 2 branches, here the right, left, the 2 particles are very close, nearby. And the point is that if you want to see what happened, you have to realize that there are different phases which are relevant here. The most interesting phase is phase 2 and phase 3. Phase 3 is the duration you keep them, say of the order of 1 second in the way you're thinking about doing this. And phase 2 is a shorter phase. It's order sort of a fraction of a nanosecond. Is the time light takes to go from one to the other, is the time it takes the gravitational field to bring the information that the particle has moved, the particle 1 has moved from its initial position to this position, bring it to the other particle. And that's crucial phase, and it's important to separate this phase from the other one. Phase 2 is dynamical, phase 3 is static, okay? And now careful, why phase 3 is static? For thermodynamic reason, because this is a dissipative system. When you see, the degrees of freedom here are one particle, the other particle, and the field. But in the field, you don't have incoming radiation, you have outgoing radiation. So the lack of incoming radiation is like a past low entropy assumption, which is a good assumption. There is you expect that there is no gravitational waves that hit this, okay? But there is a very, very teeny gravitational waves that go out, so you lose energy in this, and it dissipates. It's exactly like when you have something falling, it stops, okay? And it goes to the minimum of energy. Why? Because energy goes into heat. It heats and then it dissipates. So because it goes to its minimum heat, it goes to a specific state here. And this specific state is a static state. It stays there. It stays there for long, okay? So dynamical phase, entropy that goes up, you go a static situation, and this phase 3. So phase 2 is dynamical, as I said. Phase 3 is static. Now, in each of these branches, so there's a left, the quantum state is going to be a superposition of 4 components. And in each of these components, the quantum state, it's the quantum state of one particle, the quantum state of the second particle, and the quantum state of the gravitational field. Now, classically, in each branch is easy to see what the gravitational field is going to be, because exactly because we are at the bottom of the energy for thermodynamic reason, it's going to be just a Newtonian field. Okay, so it's, and we know what is a geometry given by the Newtonian field. This is the general relativity in the low energy, non-relativistic approximation with phi is the Newtonian field. You can go to quantum field theory and compute the state that correspond to a given potential here. There are many ways of computing the Newton potential in quantum field theory. You can use quantum general relativity. There is no reason to use the full theory here because, of course, the self-interaction of the field, you can forget about it. So you can go to the linearized theory. And in the linearized theory, it's exactly like electromagnetism. It's like Coulomb, oops, sorry. It's like Coulomb potential. This is one way of computing the Coulomb potential or the Newton potential. Is the same calculation. You think of a scattering, but you think it in the static limit. So in the static limit, you have P0 equals 0. So the propagator, you have a E from here, the two vertices. So you have an E square upstairs. And then you have the photon propagator, 1 over P square, but you're in the static limit. So you can put P0 equals 0, and you just remain with the 1 over P vector square. But you want this in position space. So you Fourier transform, and you just get 1 over X. So you get E square over X in electromagnetism and GMM over X in gravity, which is a Newton potential. This is one way. There are many ways of doing the same calculation. All right. Now, the key point is what happened next. And what happened next is you're in a static situation. Now, there is a quantum state, which you can write explicitly as a Fock space, in Fock space, or whatever you want in quantum field theory, which has an energy. Okay. And the energy is different in the various branches because it's this state here is a coherent state, in fact, and to compute its energy, again, there are many calculations you can do in quantum field theory, but it's very easy because since it's a coherent state, its energy is the energy of the corresponding classical configuration, which you can compute with completely standard methods. You can also think physically. I mean, what is the energy? What is the difference between the energy when two particles are nearby or far away? Well, it's just the work needed to bring the two particles together or separate. So difference, of course, is gm squared over d, negative when you bring them closer. So the evolution of the state here is given by I h bar, the energy by time, but the energy is different in the different states, and the difference in energy is a difference in the field, right? Fields have energy, which you can compute in quantum field theory, and this gives this the difference is exactly this result there, which has effect that one of the branches, the one where this is significant, the other is too small, has an extra phase, and this phase is just the difference of energy divided by h times t, the different energy gm squared over d. So you get exactly this key difference of phase, which I wrote at the beginning, gm squared over h d over t, which is the key quantity in the experiment. Now, you can also think geometrically, and that's I'll use later on. I don't go into details because the details are a little bit tricky, and this is a picture I use with Marius Christodoulou in our face paper on that, but Marius and Andrea Di Biagio have worked out this is more details. But I want to give you the geometrical idea a little bit more, the general relativistic version of that, the geometrical. If you think this not as a geometry, not as a field, this is a G00 component of the gravitational field, but it's a geometry that is defined by the field. The geometry is nothing else than the property of the field. The geometry define, what changes here is not the space geometry, but it's a space-time geometry. So time is affected. What a clock measure is proper time, is S, not T. And so the proper time is different than the coordinate time by this quantity here. So delta S, the change in the proper time of one phase with respect to the other one, is the Newton potential divided by the square of light. So if you're here, you feel the effect of the other particle. If you're the right particle, the two particle, you feel the effect of the one because your clock goes slower. And how much slower? Well, phi is just the potential of the other one. The self potential doesn't matter as usual, which is GM over D. So your phase changes. Now you're in relativistic picture. You have an invariant mass times c squared times the proper time, because it's relativity. But proper time is different than t because it's delta s. So the invariant mass c squared times the ds, and c squared cancel here, and you get exactly phi with gm over d times t divided by each part. So you get exactly the same result as before. But now, not as an effect of the energy in the field, but an effect on the slowing of time along the path of a particle. Are we giving different description? Yes. Of different physics? No. It's the same physics, just seeing from the field perspective or from the geometry perspective. Now, whatever way you think about that, the actual quantum state is a superposition of 4 states. In each of them, there is a state of the gravitational field. So it's a superposition of states where the gravitational field is different, or more precisely, it's a superposition of 4 states where the gravitational field in each one is semi-classical, but different, corresponding to different semi-classical configuration. So it's a linear combination of different geometries in the sense of quantum mechanics, and which is relevant because it gives interference. So that's what superposition means. You get superposition of 2 things, and the result doesn't depend on either one or the other, but when you take the model square, you get interference. So that's why there is a superposition of geometries. You can do this.
Carlo, can I just ask a quick question about that? When you say the 2 beams or the 2 branches are going to come close together with a distance d, do you mean that that would be Planck scale type distances, or do you?
No. D is the order of. I mean, you should ask Sugato or Anupama. It's the order of. It's microscopic from the point of view of 10
microns, 100
a
microns.
micron. So it's
okay.
larger than a Planck distance.
Huge by today's standards.
Yeah. For me, it's huge. For a quantum gravity person like me, it's just immense. Right.
Okay. Thank you.
All right. So it's superposition of geometry. Now, if you want to view this in the full formalism of loop quantum gravity, for instance, you can do that. You don't really gain much anything useful, because you can write this quantum state of geometry explicitly. In quantum gravity, you have a Hilbert space, and there is a basis. This basis is a spin networks, which is given by a graph and some spins, some discrete variables that sit on linked on nodes, which you can think as quanta of space next to one another. And the J gives the quantum number of the area of the surface that separates 2 quantum, and the V gives the quantum number of the volume of each of the 2 quanta. Now, this is a very quantum and thin description of the quantum, a basis of quantum states in nature of the gravitational field, which is the same thing as the of space-time itself, of geometry. But then, if you want to discrete the experiment, you need a coherent state. You need exactly like you did in perturbative. In the standard quantum field theoretical description, if you have a particle, you have the coherent state corresponding to the Coulomb or Newton classical state around it. And in loop quantum gravity, there's a well-developed theory of coherent state. So you can write, given a classical configuration, you can write a quantum state, which is a linear combination of basic states. It's a standard coherent state formulas in quantum mechanics, with some coefficients, which in principle you can know, you can compute, you have formulas for those. And then there are theorems that tells you that the dynamics, the quantum dynamics, is connected to the classical dynamics. So in particular, if this is a stationary state, it will just stay there. Nothing will happen except for a phase that depends on the energy, of course. The key point here is simply the fact that in loop quantum gravity, there is this Hilbert space. So when you have a coherent state, there's another state which is a sum of two coherent states, which is a superposition of geometry. That's what it is. So it's not that you gain anything that going to the full formalism. And if you want to compute explicit dynamics, you go into complications of the transition amplitudes, which are very complicated. But that's, it's like in standard model, in QCD, you're not able to compute confinement, but you take an approximation and you think this is viable. You have hints that this is viable, and you go ahead. All right.
Carlo,
So,
Carlo,
yeah.
can I ask a quick? So what is the capital gamma? Is it something like a Casimir, like a J?
It's a graph. It's a graph. It's a combinatorial. It's a set of points, just 1, 2, 3, 4, 7 points, and the links and the specification of the links. It only tells you who is next to who, nothing else. So this graph is not sitting in a space-time, because the geometry that it defines is given by, now you imagine that on each node of the graph, you have a little geometrical object, which is a volume given by its V, and between this, and it has areas around given by the J's in its links. So you build up a geometry in this way. So a quantum state tells you a geometry. That's the way the machine of loop quantum gravity works. Okay, now let me add rapidly some points. Something I've heard in the literature, and I consider it strongly misleading, if not even wrong when they are, I'm taking out of context, so I'm not really criticizing who wrote these statements, but the way they can be taken. First, the gravitational field is transverse because, gravitational waves are transverse. Hence, the Newtonian component is pure gauge. That's wrong, wrong, okay? Why is wrong? Of course it's not pure gauge. You cannot gauge it away, okay? If you compute look here, if you compute the Ricci tensor is 0, but the Riemann tensor is not 0, that's not flat space. That's gauge invariantly different from no field. Now, what is the confusion here? The confusion here is that when you study gravitational waves, or when you do scattering in quantum field theory, you usually go to a gauge where you gauge fix in electromagnetism A0 to 0, and in gravity G00 and G0I to 0. But that's a gauge choice. And you can't take a gauge choice and describe the Newtonian potential in that gauge, okay? Then instead of using the expression I wrote at the beginning, you make a coordinate transformation, and G00 is 1, G0I is 0, and then you put all the components in the space part. You can do that. So you can go to a traceless transverse gauge to describe the Newton potential or the Coulomb potential. It's horrible because then it depends on time, your coordinate depend on time, but you can do that. In fact, I've done it as an exercise just to be sure that this is true. The field around the mass, the Coulomb field or the Newton field, is a physical degrees of freedom, is not gauge, period. It cannot be gauged to form that way. Now, second comment, yeah, maybe it's physical, but it's enslaved by matter, is not an independent variable. Bullshit. That's wrong. It's completely wrong. Why? Well, just think of the phase 2. You have moved the particle, but the Newtonian field has not changed yet. So it's not enslaved at all. The gravitational variables, field variables, and the particle variable, the charge variable, are independent. So why then they get enslaved? Because for thermodynamical reasons. And this is because then you radiate away energy and you go to the bottom. Whoops. Shit. I always do something wrong. So look at this example here. Imagine you have a pendulum attached to a mass that can move, can slide, or can roll and there's dissipation. Here you have a degree of freedom, which is a pendulum, a degree of freedom, which is the thing that slides here, that moves here, and they're obviously independent. But if there's dissipation, once you put this in a position, after a while the pendulum stops because it dissipates away energy. So the pendulum is enslaved to the upper mass, but only because you have radiated away energy, and so you go to, it's not enslaved, just happen to be the same at lowest energy. And that's exactly what is a configuration of the Newtonian gravitational field around a mass. It's not enslaved at all. It's an independent degrees of freedom. It just happened that if you radiate away energy, you go to a value which depends on the value of the other variable. Okay. Other thing which I think can be misleading: virtual gravitons indicate a quantum phenomenon. Now, when you compute the Newton potential in quantum field theory, or the Coulomb potential in quantum field theory, one way of doing the calculation is, and in fact, the way I hinted with the Feynman graph, you're integrating over all p's. So you're looking outside. In the intermediate phase of the calculation, you're looking out of shell, outside the classical solution. But that's a purely technical calculation. The Newton field is classical, of course. The Coulomb field is classical. And the fact that you compute it using quantum field theory, using virtual gravity, doesn't mean anything. You're not doing quantum stuff because you're using that technique. It's within each branch. The physics is perfectly described by classical physics. There's nothing quantum. So where is the quantum in the QGM is the fact that you have different branches, and in different branches, there is different classical stories, which are a good approximation. So the entanglement which is revealed by the QGM is due to the fact that you have a quantum state of everything, which is a quantum superposition of two states, which can be well described semi-classically, right? So it's only when you put the two branches together that there is the superposition of geometry, there's a quantum aspect of gravity, that there's a quantum. Okay? In each branch, you could do a perfect classical story and you would have no interference. Okay, maybe I have one more minute. I don't want to go into that because it opens, it's really a separate topic, but I have a single slide about a relativistic version of QGM. I am pretty attached to this idea, so I want to mention it with a lot of caveats. The observation is the following. The QGM experiment is non-relativistic, right? We have seen it. C cancels. So it's true even if you send C to infinity. So it's non-relativistic. Could we use the same technique to measure something relativistic? Yes. And in fact, Marius Christodoulou, Andrea Di Biagio, and Pierre Martin Dussault have done an analysis of this alternative possibility and shown that it might not require too much pushing the sensitivity above what is required to the non-relativistic QGM. It's slightly different, the techniques. It is the following. Take seriously the relativistic picture where the effect is due to the changes proper time, S is the proper time, between the different branches. So this is a difference proper time in two branches, okay? It's this quantity here. Now this quantity here, as we have seen, is a standard GM square of h bar d t that characterizes the QGM. But let's look at this, how it looks in the first equality here, mc square h bar delta s. So look, this depends on a mass and a time. Delta phi is dimensionless. So I can write it in Planck units, mass of m Planck, and sorry, I should write delta s here, it's a mistake. Delta s over t Planck. Now just write delta s as a number n times t Planck, so it's m over t Planck times n. Now if, this is an if you take from loop quantum gravity the idea that any quantity of the dimension of a time, S is a time, is discrete at the Planck time, then n, it's an integer when n is small, or something like that. N is a quantum number. So it's not a real number, it's an integer. So you can imagine simplifying the delta S is just a multiple of Planck times, okay? Now imagine that this is an integer, and m is not too different from m Planck. So delta phi is gonna jump instead of being continuous. And if you go into the actual equation and do the full math, and if you measure the entanglement entropy varying a parameter, so varying the large t, for instance, instead of varying continuously, it's going to have a typical quantum plateau structure. So in principle, if this argument is correct, by having a little bit more precision, you could see this this plateau, and the entanglement is not varies continuously, but it's going to vary discretely. This would be fantastic, because not only the experiment will reveal quantum superposition geometry, but would also see the discreteness of time somehow. That's a relativistic phenomenon. Now C is definitely not canceling in this effect here. Now this would be fantastic, and I was super excited when we came out. Am I sure, in the sense in which I'm sure there is a superposition geometry, am I sure that this is right? No. I think this is plausible, but I'm not sure, because I'm not sure that delta S is really NT Planck in this sense here, and it's going to reflect in this way. Why? Because it might be that in doing this, I'm making the same mistake, which I blamed other proposal of experiment in the lab. So I'm exchanging an average with a quantized variable. I don't want to go into that. I'm trying to figure out what is exactly is the case. But in any case, I think this shows that it might be that Planck scale genuinely discrete enough time might be observed. So I've used all my time. So this is my summary, my conclusion. So I just repeat the main point. First, we have current abundant empirical information about quantum gravity, largely insufficient, but we have a lot. There are a few clear theoretical possibilities, plus some marginal, interesting, but implausible, in my opinion, ideas. Open questions, perhaps test this implausible possibility, but see a quantum gravity phenomenon. And that's the interesting of the QGEM. It definitely says, look, yes, you guys who have quantum gravity, who think that there's a quantum superposition geometry, here it is. We show an interference due to it. So a positive QGEM would definitely prove a superposition geometry, discard some unlikely possibility, shows the role of a Planck mass. The QGEM, I said, not confuse the phase 2, which is dynamics, is where the field, you need the full field to propagate. You need the full linearized Einstein equation to see that it takes some time for the information to go, and just not G00 alone. In relative general relativity, G00 alone doesn't propagate. More than one component to. It's like you need electric and magnetic field to have a gravitational waves. But then you go to a static thing, and in the intermediate case, you can use standard quantum field theory to compute the difference of energies, and there's a superposition of geometries is due to the matter superposition, which brings the gravitational field with itself for entropic reason. And by the way, when you bring the two together, when you recombine the particle, the Newtonian part of the gravitational field join again. There is still a little bit difference because there's a radiated part which is gone away. But when you integrate over it, this is obviously physically, but there's a calculation that can be done. The people in Vienna have done this calculation in the electromagnetic case. This is not going to be sufficient to decohere because they're too similar, the two gravitational fields. So this is totally under control. I mean, you can do it intuitively, you can do it in the equations. It's the final gravitational field in the 4 branches is indeed different because different radiations have gone out, but not enough to decohere. In fact, it's absolutely negligible. The Newton field is not gauged strongly, no sense at all. Whoever says it's gauged has it wrong. And it's an actual degrees of freedom in general relativity, and the role of virtual gravitons is just a technical role. What gives the effect here is the superposition of geometry. And then I mentioned perhaps one can go behind that. One last comment, which I didn't, which I skipped before. I know that many of you guys in quantum information love to think about theories which are neither classical nor quantum. I understand the interest of that, of course, because if you want to understand what is really quantum mechanics telling us, you want to single out quantum mechanics among larger class of theories and so on. From the point of view of a person doing quantum gravity, this is not very interesting. I mean, the problem is to have a quantum theory of gravity. If there's a proposal to a quantum theory of gravity using something which is not quantum mechanics, not classical, well, good, let's look at this proposal. But, you know, what is this proposal? The difficulty here is, you know, get rid of ultraviolet divergences, write equations, write the scattering amplitude. It's not just an abstract idea. So from the perspective of who does quantum gravity, exploring what about the world is neither classical nor described by quantum mechanics it doesn't seem to help at all, because it doesn't seem to say anything useful about quantum gravity. We have quantum theory of gravity. If there's another one, let's study it, let's develop it. But most big ideas goes nowhere in quantum gravity. All right, so having said all that, and having said a lot of things against things I've heard in the communities which are not quantum gravity community, let me close by saying strong and loud, which I think that the QGEM is truly one of, or even the most interesting ideas in physics I've heard in the last years. So to those of you who have been involved in coming out with the idea of developing French says chapeau, because congratulations, this is fantastic. I've been excited. I am writing a textbook on generativity, an introductory textbook, simple on generativity. And I have a small little final chapter, some sketch idea of quantum gravity. And I talk about the QGEM, because I think it's incredibly clarifying about what quantum gravity could be. Thank you.
So thank you very much, Carlo, for a very energizing and very interesting talk. And in the process, you have also shed many different and many interesting lights. So please, from the audience, if you have any question, this is the time to ask.
So yeah, I see a few. So I think Carlo has commented on many points of view. So there would be lots of questions from lots of people. So, and I see a few questions. So maybe one thing I would quickly like to ask. I mean, of course, thanks very much for all the complimentary, you know, statements. But so one thing I would like to say that we didn't really always think of this this step where we are creating or bringing back the superposition as a dissipative step. Typically, we think it's a closed system, coherent dynamics. Now, what you're saying is some gravitational wave has been radiated, though it did not, identify the components of the superposition, which could have happened. That's fine. So, yeah. So, calling it a completely open system might be a bit, danger. I have to clarify. I mean, your last, when you, in the end you clarified, that was all right. Yeah, that this doesn't decohere the superposition. And I had a quick question regarding your.
Can I comment on that very rapidly?
Mm-hmm.
Yes,
yeah.
I mean, exactly as you said. I think that in terms of the effect on the final thing that you measure, the radiated away radiation, the remaining difference at the end between the gravitational field and the thermodynamical aspect of that is completely irrelevant, because phase 2 is a fraction of a nanosecond. It doesn't produce any effect on the final thing. The effect is due to the piling up of the phase difference in phase 3, which is studied. So we can forget about phase 2, which is correctly, if you. But from the point of view of the conceptual understanding, whether there is an actual degree of freedom in the field, whether it's enslaved of matter or not, I think is important because it clarifies in which sense the field degrees of freedom and the other one are independent or not.
Okay, thank you. And I had a quick question regarding your work with Marios. Okay, so I guess you were also referring to that in the end that it may not be that it's fixed steps, but it could be random steps of the order of some time scale, right? So it would be
absolutely
then like a decohering effect rather than a coherent effect, right?
That's correct.
And the similarity with this, but this would be, if there is the time scale, is having that minimum time also consistent with Lorentz invariance?
Yes, this is thank you for raising that. There is let me dispel another common confusion. A minimum time or a minimum length are not in contradiction with Lorentz invariance. Why? Well, just think about angular momentum in no-relativistic quantum mechanics. If I take the LZ component of the angular momentum, I open a book of quantum mechanics and I read that LZ is quantized. Okay, we'll know that. It's the M quantum number. And I say, oh, this is obviously in contradiction with rotational invariance. Because obviously, if you have a length in the Z direction and you rotate a little bit, its Z component changes a little bit, changes continuously. That's wrong. So what is the point? The point is when you rotate, the eigenvalue remain the same, the distributional probability between eigenvalues changes. So when you Lorentz transform some effect, the eigenvalues, the length, and the eigenvalues of the time are the same, but of course, when you measure, the distribution probability of measuring one or the other changes continuously. So quantum mechanics permits to have at the same time symmetry and eigenvalues of operators that apparently break the symmetry, but in reality they don't.
But also the point that just the mere discretization does not mean that system is quantum. I can discretize even
exactly.
Yeah.
Exactly. The mere discretization does not mean the system is quantum. Very good. I mean, you can have a discrete geometry without anything quantum, and that is not compatible with Lorentz invariance. So what is compatible with Lorentz invariance is not a classical discrete spacetime. It's only a quantum discrete spacetime.
So Carlo, I think there are also, I mean, since you made comments on lots of points of view, so I guess there are lots of questions. So I'm sure both. So Jonathan would like to probably make some comments, and I think Anupam also. So because we have been advocating this virtual graviton viewpoint. So maybe some discussions we can have. Yeah. So maybe Jonathan asked first the question. Yeah. Mm-hmm.
Yeah, and thanks, Carlo, for a good talk. You spent a bit of time talking about unlikely alternatives, one of which was the fact that we could have a hybrid theory of classical and quantum fields and classical gravity. And you said that it was unlikely because you said that current approaches impose by fiat some, if I understood correctly, impose by fiat some domain of validity. Is that?
My argument was that you can develop a super good, super interesting formalism which describe well the approximation where you disregard the quantum effect on some variables. You consider the statistical possibility of describing these variables, but not them. And this is a formalist that describe a powerful formalist that describe well nature in a certain regime of validity when you discard something. And now you can take this formalism and make the hypothesis that is actual fundamental description of nature. And I think this step, it's essentially equivalent to say that the equations that describe this domain of validity are fundamental equations, that nature never goes out from this regime. But this, it's a constraint of the fundamental dynamics, if you want, of how the master equation should be, that it's, first of all, we don't know a master equation that satisfies that. And second, if it did, it would contradict the basis of our understanding of nature. So it's unmotivated. It's like, you know, I say, well, let me assume that the proton, the nucleus of an atom, can never be in a quantum superposition. It's true. But then the magnetic nuclear resonance is killed, and magnetic nuclear resonance is true.
So I think that misstates the case in the sense that we know that there is a consistent set of equations which keep the classical degrees of freedom classical and the quantum degrees of freedom quantum. So you don't need to impose anything by fiat. You can just, I mean, of course, one has to say there are classical systems and there are quantum systems, but once you make that split, then there are consistent master equations from which the future evolution keeps the classical system classical and the quantum system quantum. So in that sense,
I don't think that they're consistent with I've never seen explicitly, not conditions for this to be true, but these equations realized such that
there is such a thing. They do exist. But it's just a fact that such a consistent master equation exists, that it keeps the classical degrees of freedom classical. I'd be happy to send you references. Now, one can argue whether, you know, one can use these to construct a fully quantum theory, a consistent theory of gravity. But in that regard, I think one is on an equal footing with, say, theories of quantum gravity, like loop quantum gravity or string theory. I mean, we don't have a consistent quantum theory of gravity either. So,
do you that this equation could be used to describe the nucleus of an atom classically and the electron?
No, it would be inappropriate to be a fundamental theory of quantum matter because we know it's already quantum. But it's a circular argument to say, it's circular view to say, you know, that, I mean, if gravity is fundamentally classical, then it can be described by such a master equation. If it's fundamentally quantum, then maybe it can't be. But that's, you know, there's nothing, that's not a reason to choose one over the other. If there wasn't a consistent master equation, then you would be correct, but we know that they exist.
This is a longer discussion, but I think I disagree. I think I disagree in the sense, I think that is the theory that describe a classical proton interacting with a quantum electron for describing an atom, it just gives something obviously wrong when you throw the atom in a Stern-Gerlach experiment. And it's more than wrong. It's just it's violating some. Let me turn the question around. We know certain things about nature. Okay, so it's, in my opinion, consistent to try to write a theory which does not contradict what we know about nature, because we have some, I can always write a modification of the Maxwell equations, which is consistent with the Maxwell equation up to where I have tested it, and those completely different things beyond. I don't think this is interesting.
I agree for Maxwell's equation.
The incredible thing about physics is that the Maxwell equation we found, by Faraday made a little experiment, but they're true of the galaxies, they're true of the sun, they're true in, and quantum mechanics was fine, with atoms and things, and they still, so there is no hint whatsoever. There's no reason whatsoever beyond, I don't know, one page written by Penrose at some point to think that the gravitational field is classical. There's just no reason.
But there's no reason, I guess,
Yes, there is a reason for saying that it's quantum, because all fields are quantum. And so why this should be different? It's not different. It's just one field like any other. So to force the equation to say, okay, stop, let's not the usual thing work. Now, it's due to the fact that we are so used to think the geometry. I mean, someone Einstein has told that the gravitational field and geometry are the same thing. And we don't want to think that geometry is quantized because it confuses us. So we want to block it. But why? There's no reason for that. It's just, it's like, when, it's like Tycho Brahe. All planets move, the sun goes around, but don't touch the Earth, because the Earth is ours. So let's put the Earth in the center, the sun around, and everything that goes around the sun.
No, but
why treat the gravitational field different than the other fields?
I don't want to derail I'll stop, so that I'd like to continue this some other time, so I don't want to waste time. But let me just say that
I don't want to.
I agree with you that I would like gravity to be quantum, but I don't think it's an argument to say because electromagnetism is quantized that therefore gravity has to be quantized.
I think it is.
It may be reasonable, but it's not the possibility. I felt that
the possibility is not a plausibility. Possible and plausible are very different notions. So that's the entire gift of my talk. Remember, Jonathan, I'm not my talk is not. I'm telling you what is the perspective of somebody in quantum gravity. So I don't want to convince you. I'm saying, people worked in quantum gravity for 40 years. That's what people have been thinking, after having considered at very length the idea of classical geometry. It's a new idea.
No, I agree, but incorrect. But considering it incorrectly, not considering it properly, as you know. I don't disagree with you that it's plausible that gravity is quantum. The question is it consistent to have it classical? And I think for that, it's certainly consistent to have systems which are classical interacting with quantum systems. Whether that can describe gravity is an experimental question.
I never said it's inconsistent.
Mm.
I never said it's inconsistent. I said it's artificial. It pushes physics in places where I see no reason to go there. No argument for going there. The only argument is, it's so hard to think that geometry is quantized. Now why?
Because it's a precondition. This is getting an argument. Maybe we should stop and answer
exactly.
questions.
But that's can't.
Not can't, but maybe is it meaningful? Is it meaningful to think of time as quantized when we think of what physics is evolution in time? And so until you solve that basic problem, it's a bit unclear what one means.
This is the argument of somebody who hasn't got into general relativity and hasn't digested what general relativity tells us. Physics is evolution, general relativity is about evolution. Of course it's about evolution, but it's not evolution of a variable which is time, which is fixed there.
I perfectly understand what general relativity is.
But once you digest general relativity, this argument has no teeth.
So I think maybe we should shift to a few other questions. So I think maybe offline you can.
It's good just because once again, I'm not trying to convince you, Jonah. I'm just saying this is the point of view of relativists. That's what people in quantum gravity
sure.
So I just want to add something here that actually, you know, Carlos, so you are going up to one step and you still think that the QGEM is useful to, you know, to prove, but there could be other people someone who kind of completely believes rather than plausible that quantum gravity is quantum. So then kind of defeats the purpose of our experiment also. So in some sense, it is good to have theories which are consistent. So I would like there to be completely consistent theories of quantum and classical, so that we can tell that, you know, really new information is revealed, that we really show that it's quantum. So otherwise one could say that logically we falsify classical gravity and we don't need to do an experiment. So that
Yeah, I see the point.
yeah. But anyway, I mean, this remains, we can speak later. But Myung-Sik had some question, I think. So,
this is an interesting question, and maybe we can come back to this question in one of our forums. So Jonathan, maybe you may contribute in that. So, but hang around with us, because we will have some informal discussion, so we can prolong the discussion as well. So anyway, I could see Myung-Sik has some question.
Yes, thank you very much, Carlo, for your wonderful talk. And well, my question is much simpler than Jonathan's. It's just in one of your introductory slides, you mentioned about the massive slab being moved by a photon of very small length, the Planck length, but you will not, you don't expect to see any quantum gravitational effect because of the averaging. Is that right? Can you elaborate that more? Because if that is the case, so nearly all the objects have the same problem, no? Because the averaging quantum effect is averaged out.
Oh, yeah, that's well. Let me go to that specific case in particular. What is really going on is that the photon does not interact with the entire glass.
Okay.
The photon interacts with some atoms of the glass.
Okay.
One or more, or depending of the how spread is the photon. It's so it's gonna move some atoms, and then you may think that this atom in turn affect other atoms. So let's go to a simple, instead of a quantum thing. Imagine that these atoms are actually on a Planck scale grid. So space is really discrete. Then some atoms are going to jump many Planck steps, and some will jump less Planck steps, and maybe at the end of the day there will be some atoms displaced. Now, of course, if you take the average position of all the atoms, the distance is smaller than a Planck scale, but this doesn't contradict the existence of a discreteness. On the other hand, you can easily imagine other kind of experiments where the fact that all this is on a Planck scale grid has an effect. For instance, if you could send a photon with sufficiently high energy to have a sufficiently short wavelength, it would start to see that effect. So I think it's different to the different kind of averages here. I think that I see what you're saying, but I cannot come up immediately with an example. Maybe here is an example. The angular momentum of a total atom is quantized, but this is not the average of the angular momenta of the individual partons, quarks measured separately. It's something else. While the light here interact with a few of them.
So what you're saying is that so this photon interact with individual atoms, and the effect will give different effect to individual to different atoms, rather than just the mass, the center of mass of the slab.
Yeah,
we have
yeah,
to
yeah, good. Yeah, thanks. Yeah, exactly. So imagine you have a molecule and you do a Sengerlach. You get discrete thing. But imagine you take this molecule, you make it apart, and you do a lot of different Stengerlach with individual part of the molecule, and then you average. Then you don't get you get a continuum. You don't get a.
Okay.
You don't get a discreteness.
Okay, right.
So there are different kinds of experiments.
Okay, thank you.
I could see that we have another question from Hori. Please go ahead.
Yes, first of all, I want to, just because there was discussion, I absolutely agree with you that a sort of classical gravity in a quantum universe is completely artificial. Therefore, gravity should be quantized in one way or another. However, I want to come back to my first comment. The quantization of space-time, we don't have any evidence for it or necessity, because the best, theory that we have from nature is quantum field theory. And in quantum field theory, space-time is just a parameter. You parameterize your fields, and that's all. And therefore, gravity, is it a spin 2 or it is something else, we don't know, but gravity can be also just a field parameterized on this space-time, which is just a parameter space. Therefore, I don't see really any necessity for the quantization of the space-time itself.
Yes, yeah, thanks for this question. It's precise. Now I understand what you mean. So let me answer specifically. Suppose I look at a quantum gravity the way you're just saying. So I have a space-time and then I have a spin-2 field over it, and I do the quantum field theory of spin-2. That's fine, I can do that. But then I can say, in this theory, okay, the theory you just described, what happens to clocks and rods, okay? The clock and the rod interact in their Lagrangian. There is the interaction with this field.
Sorry, may I just interrupt you here? We don't know that the spin-2 field that we are seeing in classical gravity is fundamental. Maybe the quantum gravity is not really a spin-2. Therefore, maybe quantum gravity modifies the geometry, classical parameter space, geometry of parameter space in another way. In fact, I can give you a reference for something that it is preliminary, but try to show exactly this.
Okay, I don't know what you're referring to, so please do send me the reference. I'll look in and I can give them all.
I will send you the reference.
Yeah, but let me finish the argument I was doing. Suppose I take the spin-2 picture, right? So okay, so they have a quantum theory of the perturbation of the metric of the Minkowski. Fine, but then I have matter measuring the geometry. Okay, my rod, my clock. This matter, I know the action because I know the classical interaction with the gravitational field. So what is this matter measuring? My clock, what is it measuring? Is it measuring the Minkowski geometry? No, of course, because it interacts with the spin-2 thing. So it's measuring not the Minkowski geometry, but the geometry altered by these spin 2 fields. So now what do we want to call geometry? We want to call geometry the Minkowski one that my clock doesn't see, my rod doesn't see. Or we want to call geometry the actual one, which is measured by my clock and my rod. If we call geometry the actual one, which is measured by my clock and my rod, because of the interaction between my clock with that spin 2 fields, this same geometry is going to be altered and become quantum mechanical. So you see, even if you study general relativity in the book of Weinberg, which I did, by the way, and you don't think it geometrically, at the end of the day, you are full, as Weinberg at the end of the day does, into a geometrical picture and recognizing that what we call geometry, namely what is measured by our clocks and rods, is not determined by the background geometry, it's determined by the quantum field theory affected geometry. And therefore, once this is a quantum, so by the field theory geometry, and when that spin 2 field with all its self interactions it becomes quantum, the geometry itself also becomes quantum. So starting from a background space doesn't change the final result, that the geometry, which we call geometry because it's measured by our rods and clock, which are affected by quantum field, is a quantum geometry as well.
Okay.
So is there any other question from the audience? If not, then maybe I can chip in a bit. So I think, Carlo, is first of all a very nice talk, and I agree with all your comments, especially the fact that gravity is gauge and all. There were some comments been made in this community, I mean, by our community people, and I think it's good. It's great that you have dispelled those thoughts, those ideas, and I agree with the fact that what you said to a large extent. So the only thing maybe I can put in, perhaps also for the community, it might be helpful, is after all, everything is a scattering diagram. Whether we treat it in a loop quantum gravity or field theory or any version of quantum gravity, everything is happening via scattering. Now, of course, one can think about scattering as a classical football. You can play a football game or classical billiard, but the only difference between being classical and non-classical is that on one side we have a classical billiard and the other side we have a quantum billiard, where essentially the mediation which is happening is through a quantum field, and essentially, and that's, I think, which is very much coming clear from either from a non-perturbative approach or even from a perturbative approach. And I guess you would agree with this view.
Yes. Yes.
And this is what we are after. So in some sense, I think what Jonathan was also raising, that yes, so this experiment provides us with an opportunity that we can test, perhaps for the first time, which version is right, whether I'm playing a quantum football or I'm playing a classical football.
Oh yeah, absolutely, absolutely. I mean, I am. I've been critical about the plausibility of a classical gravity on a quantum matter, but I mean, let me just totally agree with Jonathan. I mean, wait a minute. Nobody has ever measured any quantum gravity phenomenon yet. So we theoreticians, I took the position of a theoretician. We theoreticians have a lot of great ideas, okay? And we're sure about everything. But this doesn't mean that we're right at all. It doesn't mean at all we're right. So I am the first one who want this happen. If I was in a funding committee, that would be my absolute top priority. And in a sense, if what I say is wrong, it's even more interesting. But it would be, in my opinion, if this experiment can be done, it's an experiment that, I mean, it's an enormous importance. I would give a Nobel Prize for this successful experiment. It's the first measurement of a quantum gravity. But if the experiment was done in a convincing way, of course, the coherence and all the horrors, I know all the difficulties.
No, this is what actually we are trying for.
If the experiment proved that there's no way to entangle particle with gravity, I would give 5 Nobel Prize. Because that means that special relativity is wrong, the general relativity is wrong, that, I mean, it's even more interesting. So both ways is interesting. Of course, I know that then there is intermediate thing, which is, well, we don't know, is that the coherence or is not, what does really happen? So I mean, life is complicated. But in the clean world of a theoretician, this is an experiment that whatever direction it goes is fantastic.
Yeah. Because it requires only quantum mechanics and relativity, nothing beyond that.
Correct.
This is the only two fundamental aspects of physics we require here.
Correct. And in a sense, you see, in my way of viewing it, the beauty of the experiment, not the weakness of the experiment, is precisely the fact that its analysis, its conceptual implications depend on the quantum field theoretical aspect of gravity. So if we believe in special relativity, if we believe in general relativity, this follows. But the experiment itself is not relativistic.
Mm.
There's nothing relativistic in the experiments. And that, it's beautiful because it's stronger. I mean, we use a non-relativistic argument to show that there is a quantum superposition of Newtonian fields, and then a relativistic knowledge to show that that's related to geometry.
Good, very good, very nice. So is there any other question from the audience? If not, then we thank Carlo again, and we formally close the meeting, but we can informally discuss. So I just stopped recording right away now.
Thank you.
Yeah, we should ask Carlo about his time as well. So if
so we are